Okay, so let me tell you about the probability distribution function. So the probability distribution function, or PDF. Okay, so let's look a little more closely at what a random variable manages to accomplish. Okay, so we had 8 outcomes, so complex outcomes. And the random variable took each outcome and just reduced it to a number, a measurement. Okay, so effectively what a random variable did, in this example, for instance, is to take my entire sample space and map it to a bunch of numbers, in this case 0, 1, 2, or 3. Okay, so we had a whole sample space, okay, omega, okay, so which was, H, 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 T, H, H, T, H, T, H, T, H, H, T, 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 H, H, T, H, T, 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 H, T, T, T. Okay, so this was omega. Okay, and our random variable x mapped this entire complex set of outcomes. Now, if we had, this is just 3 coins. Imagine if we had 20 coins, okay? So the number of possible outcomes is 2 to the 20, which is, more than 1 million, okay? So it took this complex sample space and mapped it to the very simple space of measurements, the very simple set of measurements, 0, 1, 2, or 3, okay? So that's what our random variable x did. A function that maps one set, the sample space, into another set, the set of possible measurements. So we call this set, let's call this set x of omega. It's the set of possible measurements. So what happens when you take a function and apply it to the whole space? What are the possible values of x? Okay, so the set of possible measurements. Okay, that's the set of possible measurements. Okay, so we can use, and now we just saw that we can use the random variable to define an event. So we can define the most basic kind of events. So what is the probability that my random variable takes on a particular value? Okay, so we can talk about what's the probability that my random variable x equals 0, the probability that x equals 1, the probability that x equals 2, and the probability that x equals 3. Okay. Well, the most basic events that can be defined with respect to my random variable. In other words, take all the possible values of my measurement and ask what are the probabilities for each possible measurement. So let's put that in a table. Okay. So, if I put here x of omega, so the set of possible measurements, okay, the possible values for my random variable are 0, 1, 2, and 3. Okay, and now we can ask what's the probability of each. So we call that when we talk about the probability of each possible value of my random variable, we call that the probability distribution function for my random variable. Okay, now the set of possible measurements, because we call this guy big X, we will denote by little x. So these are the little x. So we'll denote by little x. Okay? And so now we can ask what's the probability for each possible value of little x. And sometimes we sort of emphasize that these are the probabilities for the random variable big X. So we might write P sub big X of little x. So little x is just taking on the various values, 0, 1, 2, or 3. And so we're asking, what's the probability of each value of the measurement? What's the probability for each value of little x? So what are the chances that you get 0 heads in this example? Okay, 0 heads, it's 1/8. Okay, 1 head, well, what's the event? The event is this guy, this guy, and this guy. So there are 3 outcomes, so that's 3/8. Okay, 2 heads, that's this guy, this guy, this guy, so 3/8. And 3 heads is just this guy, 1/8. Okay, and this set of probabilities for the corresponding little x value, this is called the probability distribution function, PDF, the probability distribution function of x. Okay, Good. Now, certainly we can list the PDF as a table, but very often we like to plot it as a bar chart or even just a regular chart. So let me show you what that would look like. So what we do is we plot, all on the x-axis, all the possible values of x. So we have 0, we have 0. Now let me put 0, 1, 2, 3. Okay, so those are the possible values of x. And now we have here 1/8, 2/8, 3/8, and we can keep going if we had, more likely possible values of x. And now 0 has a probability 1/8. So get a bar for 0. Then we get a bar for 1. The probability of 1 is 3/8. And 2 is also 3/8. And 3 is 1/8. So that bar graph, this bar chart, represents the PDF in a nice visual way. Okay? And so we will equally call this the probability distribution function for the random variable x. It tells you for every possible value of the random variable, okay, what are the chances, what are the probabilities. Now, an interesting thing has happened. What has happened here is we had our original sample space, the original outcomes that could happen in our experiment. Okay? And then we took a measurement, and we can take more than one measurement if we want. Okay, so we took a measurement x, okay, and that transformed our sample space to a much smaller, simpler space that we can handle. Okay, and so the possible outcomes become possible measurements, possible values for the random variable x. Okay, and associated with each possible value for the random variable x is a probability. Okay, and in some sense, we can now focus on this probability distribution function as the essential summary of the experiment with respect to what we are interested in. We are interested in the number of heads, or in the temperature, if we're looking at a physical system. So we are interested in the number of heads, and the only thing that we care about is what are the possible values of heads, and what are the probabilities for each possible value. So in some sense, we've sort of created a condensed new sample space, the possible values of x, and associated with these new outcomes in some sense, but these are just the outcomes that we are interested in, the property of the actual complex outcome, okay, the property, the measurement that we are interested in, and the corresponding probability. So this is just like a new sample space and probabilities corresponding to that new sample space. Okay, and we can also define events with respect to this new sample space. So we could ask, what are the chances? What's the probability that x is greater or equal to 2? Okay, so we just look here. What's the event that's associated with that? 2 greater or equal to 2 is, this outcome and that outcome. So we have, two outcomes for the measurement x, and their probability is 3/8 and 1/8. So we get 3/8 plus 1/8 equals 1/2. Exactly the same thing that we got by working from the original sample space. Okay? But this is much more convenient. We can now compute probabilities of events that involve only the measurement x using the PDF for x, or this new, in some sense, simplified probability space. Okay? So while the true outcomes and the true sample space exist, as far as we are concerned, now they take a background seat. And what we're really interested in is the measurements that could occur, the possible values, and what are their probabilities. That's all we care about. And typically, this is what we do. We now forget about the sample space, the original experiment and the corresponding complex outcomes, and focus on the measurements and their corresponding probabilities, and define events with respect to just measurements. Okay? And it simplifies things a lot, because we don't need to work with complex sample spaces anymore. We work with the simplified measurement space and the associated probabilities. And that works as long as we only need to define and analyze events that can be defined using the measurement. So for example, x greater or equal to 2. If we wanted to know what are the chances that, you got x, what are the chances that, you got more than two or more heads, and the first flip was a heads, well, this doesn't contain that information. Then you have to go back to the original sample space. Okay. All right. Let's do one more quick example. Okay. and then we will move on to some very important random variables, measurements for complex experiments. Okay, so one more quick example. Let's do another quick example. Dice. Okay, so let's roll a pair of dice. Let's roll a pair of dice. Okay, and if we roll a pair of dice, what are the possible outcomes? So we did this last time. Die 1 can have either 1, 2, 3, 4, 5, 6. Those are the possible rolls of die 1. And die 2 can roll 1, 2, 3, 4, 5, 6. Okay, so I'll put dots. Remember my dot drawing mechanisms. Let's see how good I am at drawing dots. Wow. Boom, 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 boom. 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 Okay, so those are the possible outcomes. This is die 1. 1, 2, 3, 4, 5, 6. And die 2, 1, 2, 3, 4, 5, 6. Okay, and now, yes, complicated. 36 possible outcomes, and it's a uniform probability space, so each of these has probability 1 over 36. Okay, and we may ask, what are we interested in when we roll a pair of dice? And that's the measurement. Okay, and so let's say we're only interested in the sum. Okay, so then random variable x is equal to the sum of d1 and d2. Basically, it's d1 plus d2. Okay, you could be interested in the difference, you could be interested in the product, whatever. Okay, but we are currently interested in the sum. Okay, so what are the possible values of the sum? So let's see so the original sample space is this. What are the possible values of the sum? What is x of omega? Well, if the minimum value is 1 plus 1 is 2, and the maximum value is 6 plus 6 is 12. So the possible values are, no surprise, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are the possible values. Okay? And now we can construct the probability distribution function for the sum of a pair of dice. Okay, by asking, what is the probability that you roll a 2? What is the probability that the measurement is a 3, 4, 5, and so on? So let's see. You're rolling a 2, that's just this guy. Okay, that's just this guy. Okay, rolling a 3 is 2, 1, or 1, 2, so that's this guy. Okay, rolling that's 3. 4 is 3, 1, 2, 2, 3, 1, 3, so that's just this guy. Okay, rolling this is 4, this is 5, this is the sum 5, sum 6, sum 7, 8, 9, 10, 11, and 12. Okay, so those are the events. So let me label them. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now to compute the probability, so we can say this is P sub x of little x being the measurement. Okay, well, there's only one outcome which satisfies the sum is 2, so that's 1 over 36. And you'll see for the sum being 3, there's 2 over 36. Okay, 3 over 36, that's 3. 4 over 36, 5 over 36. Okay, and then 6 over 36. And then 5 over 36. Now it starts going back down. And then 4 over 36, 3 over 36, 2 over 36, 1 over 36. Bam! And that's the probability distribution function for the sum of two dice. And we can plot it in that bar chart if we wanted to. So let's just do that for completeness. Okay, so as a bar chart, the possible values are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and you have 1 over 36, 2, 3, 4, 5, 6. 6 is the max. So 2 over 36, 3 over 36, 4 over 36, 5 over 36, 6 over 36. Okay, and we'll just do it. So the sum of 2, sum of 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's the probability distribution function for the sum of a pair of two dice. And you can easily see from here or the table that the most likely outcome is 7. Okay, So the most likely sum is 7. Okay. Now, I just want to mention a couple of things, and then we'll go on to these very popular, very important, very common random variables. So experiments and their associated measurements that we are interested in. Okay. So, the cumulative distribution function. The cumulative distribution function. Okay, so this is related to the PDF. Okay, and you can read all about it in the text. And basically, the PDF asks the question, what's the probability that x is equal to, let's say, 2? The CDF captures the probability that x is less equal to 2. So as opposed to equal to, less equal to. Okay, so that's another common way of analyzing a random variable x is through the CDF, and you can read about it in the text. What I want to talk about, at least a little bit, is the concept that you may have more than one random variable. Okay, so here we have in the same experiment, we have the number of heads and the indicator of whether the coins match. Okay, so you can have more than one random variable. So you can have more than one random variable. And there's no harm in that. There's nothing wrong with that. And so you can analyze, complex events like, what's the probability that something is happening with one of the random variables and another random variable. Okay. Now the typical way we condense the entire outcome space when you have more than one random variables defined for the same experiment is using what's called the joint probability distribution. So this leads to the joint probability distribution function. Okay, that's called the joint PDF. So again, I'm going to ask you to read the text for that. I'm not going to spend so much time on that. Okay. What I would like to talk about is what about when you have the random variables from different outcomes that are completely independent. So let me give you an example. Okay. So independent random variables. Okay. So let's say you toss 5 coins. Toss 5 coins. Okay. And then independently, okay, you toss another independent 5 coins. Toss another independent 5 coins. Okay, so now we can measure for each of these experiments, so independent experiments, and this is typically the way we will encounter multiple random variables. Okay, but for sort of independent experiments, you've got, you can measure the number of heads in the first 5 coins, so let's call that x. Okay, the number of heads in the first 5 coins. Excuse me. Okay. But you can do the same thing for the second 5 coins. Or you might not measure the number of heads, you might measure whether or not all the 5 coins match. You may make some other measurement, but for the, whatever it is, we could call it a random variable y. Okay, and for simplicity, let's imagine that we measure the number of heads in the other experiment. Okay, and now we can ask, what is the probability that x equals little x and y equals little y? Okay, so for example, what is the probability that x equals 3 and y equals 2? Okay, and you see this is related to a joint probability distribution function, but we're talking about the special case where the experiments are in some sense independent. So what we say is that these random variables are also independent in such a situation. Okay, and the probability of something happening with random variable x and a totally independent random variable y, it's exactly what we would expect. It's the product. Okay, so this is going to equal the product that x equals x and y equals y. And this is the PDF for x. And this is the PDF for y. Okay. And we say that these random variables x and y, the random variables x and y are independent. Okay. And it's because we can compute the probability of an and using a product. And that's especially the case when the experiments are totally independent, like here. Now, you can define independence even for the general case where, the random variables make measurements on the same sample space, and that's where the joint probability distribution function comes in, and so on and so forth, okay? So read all about that in the text. But for our purposes, whenever we encounter independent random variables, it's usually because those random variables are measurements in totally different, totally independent experiments. Okay, so what have we talked about so far? Well, we've introduced the concept of a random variable. Don't panic. It's just a measurement. You run a complex experiment, you get a complex outcome, you take a measurement, you get a value. Okay, and so a random variable is effectively just a function that maps outcomes, complex outcomes, to values, i.e. measurements. Okay, it's just a function that maps a set of outcomes to a set of numbers. Okay, and now once you view it that way, then the set of possible outcomes, so the set of possible values for the random variable becomes your new effective sample space, and the associated probabilities become what's called the probability distribution function for the random variable, and so the random variable and its associated probability distribution function summarize the experiment with respect to what we are interested in. So we can focus on what we are interested in, which is the measurement. And usually at that point, we can now forget about the sample space, which is complex, and focus on the possible measurements and their probabilities, or the PDF for the random variable. Okay, and that's the value of the random variable. It summarizes a complex experiment into the simpler PDF that we are interested in. And then we talked about, the possibilities where you have multiple experiments and multiple random variables coming from each experiment, multiple measurements from each experiment. Okay? And the fact that if the experiments are independent, then the random variables are also independent, and you can compute probabilities of and by just multiplying probabilities. Okay? Now, let's go and talk about all kinds of different random variables. So we will do the usual speed erase.